this is a probabilities game, right? So when you conduct an experiment, there's a certain probability of success, P, and there's a certain number of experiments you can conduct per unit time, N. And so we need to increase both the P by developing better generative design algorithms that focus the limited experimental bandwidth on the most promising candidates and really identify those diamonds in the rough, those needles in the haystack. And we also need to increase N, meaning the throughput, the experimental capacity, how many samples we can make and characterize and deliver high quality information, not just garbage in, garbage out. So it's increasing P, increasing N. That's achieved by that balance between computation and high throughput experimentation integrated into autonomous lab settings. If you think about the challenge of discovering a new material, you have order 10 to the 10 inorganic crystalline stoichiometric solids and order 10 to the 100 organic materials. Down selecting that huge number to a number that is experimentally tractable, and then repeating each candidate material under different reaction conditions to be able to test it properly. That is the challenge. So it's a down selection process. And if you think of it as a state space, you're going from a state space of 10 to the 10, 10 to the 100, down to order 10 to the 3. That down selection process, if done well, can focus our limited experimental bandwidth on the most promising candidates, accelerating the rate of new materials discovery. If it's done poorly, we spend a lot of time and yield no results at the end of the day. The challenge is we don't yet know how exactly to do this down selection. And so we're at the stage of coming up with hypotheses for how we can down select. Is it using a pure play neural network, a generative design algorithm, a diffusion variational autoencoder, or is it brute forcing our way through ternary phase diagrams, applying series of filters, or is it taking known compounds and modifying them using a genetic algorithm approach? We don't know exactly which path might yield success, both in the near term, but also transformative success in the intermediate and long term. And so we're attempting various ways of solving the problem and doing the experiments and seeing which pathway yields the greatest rate of progress per unit time and investment in different material subcategories. I think what makes this really hard is in, say, drug discovery, you have a limited number of atoms and a limited number of synthesis methods to access a wide range of different small molecules. In inorganic crystalline solids, we have specialized synthesis and characterization tools for each materials class. The tool that I will use to make phosphides is not the same that I will use to make halides. And so it naturally forces a certain amount of speciation and specialization in each laboratory. So our ability to cross-pollinate and learn from each other is more limited. I think forums like this at the MRS allow us to come together as a broader community, share learnings, and hopefully accelerate the learning in each of our sub-communities. The vision long-term is to be able to take a grand challenge problem that demands a material with, let's call them, a variety of constraints, many of them contraindicated. So for example, a material with high electrical conductivity but poor thermal conductivity. Usually those two parameters scale together. If you want to break that symmetry, you have to really think out of the box. So coming up with an algorithm that will guide the experimentalist toward the most promising candidates, that's the ultimate vision. Working backward from there into near-term wins, I think the nearer-term wins, honestly, are with simpler problems that might demand smaller modifications around what actually works today. So we're drawn by that long-term vision, we're drawn forward toward it, but we need to think practically, what is a laddered approach that will get us toward that big win? What are some of the small intermediate wins that we can have along the way that will sustain the enthusiasm, the funding, and allow us to assess whether we're realistically making progress toward a larger goal? I think what draws a lot of researchers to the field of autonomous research is this idea of acceleration. They want things to go faster. We're all frustrated at the slow rate of progress in manual processes. But that also can trip us up, because to realize an autonomous lab takes a lot of patient investment, and the return on investment looks a lot like an S-curve. You put in a lot of time up front before you start seeing the results. When the results start coming, they're amazing, but it takes a long time. A lot of people don't realize this. They get into it thinking, oh, accelerated, I'm going to get accelerated results. And it's not the case. If you move with too much haste, you wind up tripping up. In Cantonese, there's an expression, yok chok sapata, which means move with haste, don't reach. I myself, as a technical manager and at times a practitioner of this field, I've made an abundance of mistakes myself. Even as recently as a year ago, I was overly optimistic about how fast progress we could make. And this ended up tripping up our team in terms of how we managed our projects and delivered on our results. So I think this is also an opportunity to share some of those stories, to make it accessible to everybody. I think we can all resonate with certain shortcomings and learn from these experiences collectively so that we can do better executing research, planning research, and managing the research transition.